In this appendix, Appendix 44.7, we're going to review just very quickly some of the basic algebra you need for these lectures that would be useful. First of all, you know the fundamental relationships that we have, and generally we take those relationships and try to derive simpler or equivalent relationships. For example, we may have x plus 2 is equal to y plus 2. And since we have a plus 2 on both sides of the equations, we would like to do something to one side of the equation and do the same thing to its equal. This is the traditional aspect of what we do in algebra and in mathematics. We look at equality between things, and sometimes we look at inequality. One thing can be greater than the other or less than the other or some other relationship. But with equality, if two things are identical, we can do something to one of them and do it to its identical partner, and we still have an equality left. And if we do that here, you can see the 2's are gone, and we get the result that x is equal to y. That type of manipulation is the foundation of algebra. Equations are solved by doing the same thing to both sides of the equation. 4x minus 3 is equal to 2. We would, quote, simplify and solve that equation for x by adding 3 to both sides. 4x, therefore, is equal to 5. And then dividing both sides by 4, giving us x is equal to 5/4. You should be familiar with powers. And of course, x to the a times x to the b is equal to x to the a plus b. So when we multiply numbers, we add the powers or their exponents. If, for example, on the other hand, we have x to the a to the power b, then you can convince yourself very rapidly that that's x to the a times b. An example of this, we might have 3 squared times 3 cubed, and that product of the two would be 3 to the 5th. And you can see why that's true. This really means 3 times 3, and 3 times 3 times 3. Well, that is 3 times itself 5 times. But if we had 3 squared to the 3rd power, that means multiply this by itself 3 times. That'd be 3 squared times 3 squared times 3 squared, and sure enough, that would be 3 to the 6th, exactly by multiplying the 2 times the 3. You should be generally familiar with factoring. And if we have something like x squared minus y squared, it's obvious that that is x plus y times x minus y. This is what is called factoring. We can also go the other way and expand this out and get this alternative expression. Sometimes we want to factor because we want to use part of the factor to do something, maybe the x plus y, and divide it into something if this is in the denominator. Factoring can be very difficult. In fact, some of the most difficult problems are to factor very, very large integers and see if they're prime. Very outstanding problem in mathematics. Let's look next at quadratic equations, because we'll be using quadratic equations. The quadratic equation says that a constant times x squared plus another constant times x plus another constant may or may not equal to a number. Let's let this equal to 0. If it were a number, we could subtract it over here. Now the question is, we know how to solve this, which is a simple linear equation like we just solved. But how do we solve this, which is a quadratic? It means it's x squared. This is a polynomial, and this polynomial can be solved for x by a well-known formula. X is equal to minus b plus or minus the square root of b squared minus 4ac, quantity divided by 2a. Often when I divide this by 2a, I may or may not want to put it under the square root and make it 4a squared. But when I do, it would be minus b over 2a plus or minus the square root of the entire thing, b over 2a again, so therefore it's squared, because I've put the 2a under the square root. I've also put it under the square root here, which means I've got 4a squared, and so it'd be minus 4, and the 4 will cancel, a will cancel with one of the a's, and I have c over a. So sometimes it's written this way. Linear equations, such as y is equal to, I'll have to move the paper, mx plus b, gives an intersection. If I plot this, here's x and here's y, and I plot this function where y is equal to this, in fact, you can see that if x is equal to 0, y is going to be equal to b. So this height is b. Also, you can see that the slope, if you know calculus, then you can see an infinitesimal change, dy, is equal to m dx, and the infinitesimal change in b is 0. So dy over dx is equal to m, and therefore this is equal to the slope, dy over dx. And so m gives us the tangent of the angle, which is often called the slope of the line. We can look at linear equations like that. We can also look at simultaneous equations. And for simultaneous equations, we may have one equation that looks like this, another equation that looks like this. And you can see that if both of these equations are conditions that must be met, they're exactly 2 points in the plane, 2 values of x and y for this will be true. It is possible to have situations like this where they never cross, and that these simultaneous equations have no joint solution. Depending upon what the order of this is if it's a straight line or it's a parabola or a hyperbola, second order, or a cubic, which might be represented like this, that can tell us what the number of solutions might be. And you might have that many, or you might have less. As you can see, a straight line crosses this cubic equation at 3 places, but it can also cross at only 1 place and give actually 2 imaginary solutions here. We next ought to talk about logarithms, and let me get a new sheet of paper for that. So this would be 44.7b. Let me go over logarithms very quickly, because you will be responsible for knowing logarithms. The logarithm of a plus the logarithm of b is equal to the logarithm of a times b. This was really very useful back when we could make tables of logarithms and we could multiply very easily by adding their logarithms together and then taking the antilog. By that same token, if we used a minus sign here, log a minus the log b, this was equal to the log of a divided by b. So if we wanted to divide two very large numbers, we could take their logarithms, subtract them, and then find the antilog. In other words, do the inverse process, and it would give us the quotient of the two numbers. What is the log? Well, basically, if we think about it, if we say y is equal to the log to a given base of a given number, this means or implies that x is equal to a to the power y. In other words, the logarithm is an inverse process for exponentiation, where the base is the number that's exponentiated and the logarithm is the exponent. So in general, logarithms are exponents. And that's why when you add them, it represents multiplication, just as we saw when we multiplied x to 2 powers, and it multiplied the two parts. Normally, we pick only certain bases, and let me tell you what those bases are. We often use logarithms base 10, we use the natural base, logarithms base e, and sometimes logarithms base 2. This is for information theory, for computer science. This is for general science, and this is for business, stock markets, things of that nature, and simple work where it's easier to think about the powers of 10. This equation here is very important because it explains what a logarithm is. Because you already understand that x could be a number a to a power y. It then follows that y is equal to what? How do we solve that equation? Well, y is equal to the logarithm base a of the value x. Another useful equation is that the log base A of B is equal to, in other words, how do we find these weird base logarithms? It's the log base E of B divided by the log base E of A. Now, logarithms base E are in every computer, in every calculator, and we often write log base E as ln. And this means natural logarithm. So you will see the expression ln standing for log base E. Also, many times we write the log to mean log base 10. So if you see log just written this way, it's somebody who never experiences logarithms except to base 10. Logarithms to base 2 are very close to log base E because, as you may recall, E is 2.7, 1828, 1828, da 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 da. And so E is not too far away from 2 itself. So a log base 2 is useful in information theory because you have ones and zeros. You have a base 2 type of information, and therefore the logarithm of that is very important. Something I'd like to discuss with you is the fact that socioeconomic variables, something like population and electric use, how much water is used in the world, things of that nature, these things are generally exponential in time, and therefore their logarithms are linear in time. We could pick 1,000 different things. We could look at something like how much gold is available to all of society. We'd find it some kind of linear over time. Going from prehistoric times, it's probably going to be a straight line on a logarithmic scale, meaning it's increasing exponentially. Now, it might increase very slowly. This scale might be incredibly tilted down this way for something like gold, but for population, it might be up like this. Now, that's not guaranteed, but if we plot a function that is exponentially increasing and it becomes a straight line, it's very easy to discern that this is a straight line. Just put a ruler next to it and see if your data points are lying on a straight line. It's very hard, on the other hand, to see if this is truly exponential. So what we do is we take the logarithms of these values, plot those logarithms, and see if it's a straight line. The straight line gives us exactly what the exponent is for understanding that. Now, in addition to that, population, electric use, and so forth are exponential in time, and therefore their logs are linear in time. But, on the other hand, the second piece of knowledge you need is that the ratio of variables is usually relatively constant. Let me give you an example of that. If we went back to the year, this is very hard to believe, but let's go back to the end of the Civil War, 1865. And let's look at how much energy was used in 1865. And let's plot that every year to the year 1900. You'll find, if we plotted the log, that that log would increase as a straight line. In fact, it will be a straight line all the way up to the year 1975. You can predict what the energy use is in 1975 by the energy use from about 1865 to 1900. So I mean, it's not perfect, but it's very hard to change the rates of things, like the rate of reproduction, population growth, the rate of use of electricity, energy, and so forth like that. But to get back to what I was about to discuss, I got a little bit sidetracked. If I look at ratios of economic variables, they're relatively constant. So if we look, for example, over a period of time in 1865, 1900, 1925, 1950, 1975, if we were to look over a period of time like this and say, what is the fraction? Now let's look at the fraction of percentages from 0 to 100%. what fraction of our energy is used for, let's say, what fraction of our income is used for food and what fraction for medicine, we'll find that those are very, very flat curves over very, very long times. More recently, our medical expenses have increased as a fraction of what we're doing. Now, the first thing you might say when you see that is, well, think about something like transportation. Certainly, back before 1900, we had mules and we had horses and carts and carriages. We didn't have the horseless carriage. We didn't have the automobile. We didn't have the plane. But it turns out that people spent about the same amount of money on their horses and the care of their horses and the veterinarians that they later spent on their cars. That they spent the same amount on the roads as they later spent on the highways. So the fraction of our entire worth that we spend on transportation is relatively constant. Knowing those two things is extremely important to look at socioeconomic theory and variables. Namely, most things will be such that their logarithms are linear in time, meaning they increase exponentially, so when I take the logarithm it looks like a straight line over very long periods of time. Likewise, percentages of things, percentages of uses, such as in the United States, what percentage of our energy is spent on commercial and residential usage of electricity? You won't believe this? It's 2010. That number has not really changed more than 1 point since 1973. So if you look at that fraction, it didn't change. So those are important computational tools.